My name is Ian. I run a consultancy. It's about 10 years old here in the UK, mostly based up in London. I work on a range of data science problems, got a couple of people working with me, and one of the problems that I face running my own consultancy is the requirement to go into a client's office and work on a number of projects in a tight time frame and iterate on a wide variety of problems. And often the quick iteration speed that Python gives me is wonderful until I hit the bottleneck where I want to process 1 million of those things, and then it will take overnight to run. And so I spent a lot of time working on high performance options so that I can quickly scale up and run things quickly. So a part of this involves profiling, so doing a lot of profiling to understand why a system is running slowly, and not thinking in large engineering heavy terms about setting up a big profiling framework for one particular system and keeping an eye on it, but instead diving in quickly, so getting results in 30 minutes to understand out of 10,000 lines of code where my particular bottleneck is and how to solve it. And that's something I'm going to cover in this talk because it's something that engineers often avoid because it's a little bit of a pain to get set up. And there are some good options, and I think people avoid some of those options. So I'll talk a little bit about that. And then I'm going to look at ways of speeding up the bottlenecks that are uncovered, looking at both just-in-time compilers, so PyPy, for example, and Pythran and Numba, and also static compilers, particularly Cython and Shedskin, and then some of the options around there. And there's a good reason to think about the need for speeding up the bottlenecks in code, both in terms of CPU execution time and RAM usage. And that's because, certainly for me, if I've got a problem and it stretches on more than one machine, all of a sudden the problem doesn't fit in my head. And so I have to start thinking about cluster management and maintenance of my system, and in particular, reliability of data, latency issues, and all the rest. Really, I just want to boil a set of data down onto one machine where I can do some analysis on it. So it's always quite keen in my mind to think about the largest data set I can work with that fits inside 8 gigabytes and 4 cores and a couple of hundred gigs of SSD storage, say. So it's a different scale of problems to some of the problems discussed by other speakers and other teachers here. And then there's this final point about high performance, so keeping the team speed high. Just because I can work with, say, Cython and wonderfully exploit at a low C level all the cores on one machine, heavily compiled down with all the optimizations to make a piece of code about as fast as it would be if I coded it in C, if no one else in the team understands it, then the bus factor of this particular bit of analysis is 1. So if I get sick or get knocked over by a bus, then no one can pick this code up again. And I've seen startups massively hindered by having a CTO understand how to make a critical piece of their infrastructure work as fast as possible and then leave, at which point the startup is dead. So keeping the idea of the velocity of the team in mind, as well as the velocity of progress with the code, is quite important. And that helps to inform the landscape that we're looking at. So I'm also working on a book on high-performance Python. So the slides here are taken out of the chapters on profiling, static compilation, and JITs. I've got a mailing list. So we've got some announcements there. The rough cut of the first few chapters should be online soon if you're in O'Reilly. We tried to go for speedy snakes as the subtitle, but we weren't allowed that. I tried to get the image changed so we could have a wide-eyed snake with crazy big eyes and a turbojet on his back, but O'Reilly don't do cartoons. And so then we tried to go for hypersonic herpetology, but that's too Latin, so we just had to go with practical performance programming. Show of hands, how many of you know the C profile module? I'm guessing most of you. How many of you know the runsnake module? Okay, a fair number of you, good. So runsnake is a simple visualizer for the C profile module. It gives us this nice box plot where you can see where the majority of your time is spent. In this case, a function is taking most of the time, and then there's a call to the abs function in there. That takes a fair chunk of the time, about 25% of that routine's execution time. What we can't see is what's happening in the other 75% of the execution time inside that function. And there's no way to drill in with C profile. It just tells us the overall runtime of the function calls, not the individual Python lines inside the code. So that's not so useful, but it gives us, it's kind of a blunt tool when you've got a complex system and you see many, many thin lines and then one large block in the middle, you found your slow function, so it's easy to go and work on that. Another downside of cProfile is that you don't get to do any argument analysis. So if you've got the same function being called from several different points, you get the cumulative time that the function is being called, but you can't see which set of arguments are causing some kind of pathological behavior, so that one part of your runtime's execution goes really horrible. And that's a problem that I haven't seen addressed anywhere in any of the profilers at the moment. So Line Profiler from Robert Kern. This, I think, is one of the strongest profiling tools. Who here knows Line Profiler? OK, some of you good. So Line Profiler is pretty amazing. It's written in C. It's a Cython? I'm not sure. It's written in C. So it hooks into CPython at a low level. It does slow your code down when you're running it, but it does instrument every single line. So if you come from a Visual Studio background, you'll be used to this kind of thing. But it was a wonderful find when I came across it in the Python world. One of the nice things about it is it annotates every single one of our lines of code. The cost is you have to put a decorator in the top. That means you put a decorator in, and then your unit tests start to fail because the unit tests don't inject that decorator. So there's a little trade-off between getting the correctness of your code working versus profiling it. Because if you're profiling and optimizing and not running your tests, you could end up spending a day wonderfully optimizing a function, being really proud of the result, and at the end of the day, taking out the app profile decorator, running a unit test, and realizing you've got a very fast but wrong solution. It's something you don't want to be doing. So one of the nice things about this is that you get to count the time cost. This is normalized to some constant that's not shown. The time cost of each of the lines of execution. But what you really care about is the percentage time spent on the various lines. So we can see that this inner loop in this Julia set calculation is the really expensive part. And out of these 3 lines, even the int increment is quite expensive due to the dynamic nature of Python. And this outer loop here, one of the downsides of Line Profiler and all the profiling tools is that we've got a compound statement. We know that this statement is one of the slowest in the code, but we don't know which part of it which side of it is the slowest. And to deal with that, you have to break it down and look into it some more. As far as I know, there's no way past that with Python tools at the moment. But this is definitely one of the best tools for profiling code for CPU time. That brings us on to the Memory Profiler. This is a relatively new tool. Who knows Memory Profiler? OK. So this is written a couple of years ago. And Memory Profiler has basically the same interface, same decorator, the same kind of output. It uses the psutil module, so it's looking at the process space and talking to the operating system to get process details. And here we're checking external memory increments and decrements for the process over time. So we're not talking to Python. We're not asking it, how big is that object? We're saying, you've done a line of code. Operating system, tell me what the external effect is. And so due to caching and due to over-allocations, we can see quite large changes in memory usage. But also if you're using C extensions, which don't tell the Python interpreter how big or small their memory usage is, we get to see it because the operating system tells us what's going on. So in this particular case, the memory output is not so useful here. We get to see that allocating 1 million integers of a singular item 0 costs 7 meg, great. And if we build up a number of several million intermediate objects, that costs another 32 meg worth of memory. Not so useful in a smaller case like this. Very useful if you're just looking in IPython with a magic, so %memit. You can give %memit an argument, and it will tell you what the process space changed by. So 7 meg for a singular object with 1 million indexes, and 1 million different integers cost a different amount of RAM, because you're making 1 million different numbers at this point.
Sorry, this is Python 2, right?
This is Python 2.7 I'm running this in, yes. I think there's no reason why Memory Profiler wouldn't run in Python 3. Line Profiler, I don't know if it's compatible with Python 3. Something that comes out of Memory Profiler is mprof. And so here we can look at the dynamic state of a system over time. So here we're just looking at, this is some pull requests from the scikit-learn project. So this becomes a visual communication and discussion tool. And this is a little bit exciting if you're thinking about, you've spent a day working on something, you really understand the memory behavior and the CPU behavior, you've really got it in your head. Now you've got to convince your boss and your associated team that it's worth making this large set of code changes to improve a chunk of code. How do you describe the overall behavior of your system over time? So here, with mprof, I've taken the labels out. They're off. I've just stripped those out. But you can see the brackets where the labels will be attached, telling us what each of these code blocks are doing before a particular change. And that's about 3 gigs worth of RAM being used here, with lots of cyclic allocations, and then about 2 gig after this change has been applied. And actually, if you follow that pull request, you'll see that this was the proposed fix. And then the discussion started at that point, and then there was much more discussion trying to understand the root cause of the behavior and the CPU implications as well as the memory implications, leading to a couple of fixes that came out of this. So it becomes a nice discussion tool for communicating in a team. And I think that we can use Memory Profiler as a generalized resource profiler. So I've begun talking to the authors. I've been playing with recording, rather than using psutil to record memory usage, I've been looking, in this case, at I/O usage, so just looking at the number of bytes sent in and out of network interfaces. So this is a single process serially fetching documents off the web, so utterly naive case, takes 60 seconds, and then 15 seconds with 20 processes or so gathering in parallel. I mean, this is it's a very simplistic use of this, but we get to see shorter time, more bandwidth being used. And if we run it at full max capacity, we end up topping out the network allowance. And so we get to see the external constraints imposed upon our machine with this. I've also been looking not just at I/O over the network, but I/O from the disk as well. That's kind of interesting when you're doing a lot of reading and writing of data, beginning to think about contention. And I think we can begin to expand this just into this more general tool where we can label our Python code and really understand what's happening. And so to close off the profiling, we can do CPU and memory profiling, and with a little bit of hacking, this is like 5 lines of changes in the memory profiler. We can begin to profile disk read and writes and network read writes. Via psutil, we can also look at memory maps, so shared memory blocks, and file handles. So maybe we begin to have an external debugger looking at pathological behavior at certain points in a system when external file handles go crazy big. And instead, we can start to label our code and really understand what's driving that kind of behavior. And that might be really useful if we're picking up projects that we haven't worked on before, and we really want to get an understanding of this new bit of code rather than just sitting there studying it. We can look at network connections, and I'm really interested in the idea of cache utilization. So I've been using perfstat to look at to get the CPU to tell me about the CPU performance counters. And one thing it can give you is the average instructions per cycle. So if you're inefficiently using the cache, you'll have a low average number of instructions being executed. And if you're using, say, nice numpy routines, you'll have a high number of instructions per cycle being executed. And if your data set is too large, it won't fit into your level 3 cache or your level 2 cache, then you'll end up with a lower average execution speed because the CPU, as Francesca was talking about earlier, the CPU has to wait for the data to be pulled in from RAM over that long, slow bus into the cache, and then over the shorter but quicker bus into the CPU where it can be used and then shuttled back again. And I think the idea of dynamically profiling and listing which bits of our code are using caches effectively and ineffectively is a pretty important idea. So I'm going to finish off the profiling bit there. Any questions on this stage?
Just in terms of like the pointers you've made there for future directions, I mean, that all sounds extremely interesting. Is there any, I don't know, is that like a project in its infancy, or is that going to actually go forward?
I've written some code. It works. Fabian said, that's great. How about we start a new project? And I said, well, I'm writing this book. How about when I've finished writing the book? So we've said we'll come back to this in a few months' time when the book is finished. I think it's pretty interesting, so I want to push on with it. Certainly, I'll push the code's not there yet, but there's no reason why the code can't go out in its current very hacky state. I've done nothing on the libperf bit apart from look at the library. It looks like I can hook in where I want to hook in and use this, and I use perfstat externally to run a Python interpreter and then investigate performance. I don't see why I can't hook it all together, but I haven't done that. Okay, yeah, and so in the book I've got a little bit on mocking up a dummy decorator for both line profiler and memory profiler, and I'm hoping that can get included back into those projects, so just so you can copy paste it off the man page or whatever. Because there's nothing worse than after a day optimizing your code than going back and realizing you've busted your tests and you're an idiot. Okay, so moving on to making your code go faster. Cython will be the tool that, hands up, Cython, I'm guessing most of you know Cython. How many of you used Cython in anger? Okay, only a couple of you use Cython in anger, fair enough. So there's a good reason why you won't use Cython in anger. It's great, it is the best tool, you do get the best performance out of your machine. It's hands down, I think, the best tool to make your code run fast if it's CPU bound. The reason you will have problem using it is that you have to go through and annotate your code, so all of the bold bits are the annotations that we've added in. This is the Julia example again. So you have to start writing C-like code, so it won't run inside Python anymore. You have to compile it and then import that module and call the module. That means that your agility goes down, so your ability to quickly hack on this code or step into it with the normal debugger or anything, that all disappears. So it becomes harder to maintain and experiment with your code. So it's great if you figured out this is the function. I've got this module, I've got a function, I take the function out, and I've got a set of them maybe in a separate module. This is exactly what needs to be optimized, and I don't need to change it. Then it's completely the right solution. But it's in competition with Python's goal of being agile and lightweight, and so that makes it a bit more difficult to justify, particularly when, for example, you speed up a physicist code, and then he says, great, how do I maintain this? And you say, well, now I've got to teach you C compiling. And then all of a sudden, it's a bit difficult handing it over and leaving it with somebody else. So that's a bit of a drawback. Just to give you an idea here, so this particular bit of code, before adding any annotations, it runs in CPython in 12 seconds. Adding in these annotations and compiling it with Cython brings it down to 19 seconds. So that's a 2 order of magnitude improvement, or 50 times speed up. And converting it from Python lists into numpy arrays, so really memory efficient arrays, only improves the speed overall by a small amount. And that's just because once you've and this is it's a silly usage of numpy arrays, memory efficient usage, but silly usage. If we use numpy arrays here rather than lists, all we're doing is dereferencing array elements into some primitive types and then looping 34 million times in here tightly on some primitive types. So the fact that we had the data stored in a list or a numpy array doesn't really come to play into this. Now, Cython, I've mentioned that it's the best way to get the best speed up. It's one of the 3 tools that hooks in with OpenMP. So with OpenMP, you get to use all of the cores on your CPU, as long as you can get away from the GIL restriction, so you need to step outside of the global interpreter lock. So if you are working on non-Python code, so particularly you've stored your data in a numpy array, which is a large block of bytes, which can be controlled by the Python interpreter, but doesn't have to be, we can then, at a certain point in the code, use the no-GIL parallel context manager to step outside of the GIL. We suspend the GIL temporarily, and then we use the p-range operator in Cython, and that just says, give me as many threads running at a hardware level as are available on this machine, and then run in parallel. And once we do that, our runtime drops from 0.15 seconds to 0.05 seconds. It's not quite a full 4 times speed up on the 4-core machine I was using, but it's pretty good. It's quite a nice improvement. The reason it's not a full 4 times improvement in speed is because, in this particular case, the Julia set, it's unpredictable how many iterations are required at each of the points, which is why we get the pretty plot coming out of it. Because it's unpredictable, the utilization of the cores isn't as perfect as it would be in a fully, embarrassingly parallel, equally workloaded job. So stepping on to Shedskin, who knows Shedskin? 1, 2, 3, okay, right. Now we're working at it. So Shedskin is a wonderful project. It's almost known by nobody, which is a real shame. There are some limitations around it. Here we're looking at a bit of debug output. With Shedskin, you point Shedskin at a module. In that module, you've got a little main routine which calls the function that you want to compile. Shedskin looks at the function, looks at the types in that function, looks at the function you're calling, and performs a full type annotation of the function. So you do no manual labor at all. It does it all for you. It then spits out some C, you run make, it gives you a compiled.so, you import that module, it's just a compiled module. So it's just like Cython, only you do no work. So it's wonderful. The limitation is it doesn't work on numpy, and it doesn't use the byte array interface, the memory view interface. So if you're using a large block of RAM, so you've got a Python array, not a numpy array, just a Python array, which can expose the bytes hidden behind it, that can't be used separately by Shedskin. And what Shedskin does is takes the memory space in the Python world and copies it all to a fresh copy. So if you've got a gig of RAM, you end up with 2 gigs of RAM. Shedskin works in the C world on this other gig of RAM and then passes a result back. Now, if you compare the runtime execution on this Julius example with Cython and with Shedskin, you end up with the same runtime if you ignore OpenMP. So on the single-threaded version, the same runtime. Shedskin's a tiny bit slower, and that's because it's copying over a large amount of data. So it's the memory overhead is the only thing that's the difference between the two. So, and that's this 0.02 seconds down here difference in the runtime. It has occurred to me, and I'm not quite sure why anyone hasn't played with this, why can't we just take this fully annotated output, this is the debug output, but there's an AST built up inside Shedskin. Why can't we take that and just write out a version that's Cython compatible? It wouldn't necessarily be correct first time, but it will give you a hell of a hint as to how to get it correct. And so the time to teach someone else to start using Cython would go down massively. And it would open the door to them moving into the numpy annotations, I think. Who knows Pythran? OK, good. So Pythran's really interesting. So Pythran is a bit like Shedskin, but it works with numpy, and it works with OpenMP. So I think it's the best of all these worlds right now. You do have to do a tiny bit of work. You do a one-line annotation. It's a comment. You put Pythran export my function, and then some types. So in the list example, it's int, a complex list, and a complex list. And then everything else is exactly as it was before. You do Pythran, my module, you get a compiled library coming out the other side. You run it, and then it runs 0.4 seconds. So it's not quite as good as the Cython output right now, but it's pretty good. I have a geek confession, so I'll set the scene. Valentine's night, 1 a.m. I was filing a performance bug for this particular bit of code. My wife was out of the country, so I was allowed to just sit there and play. The reason I mention that is that I filed at 1 a.m. The next morning, the authors had come back with a new tarball fixing that performance bug. They didn't like the fact that I'd found anything wrong with this. And so it was running at, I don't know, 0.7 seconds. And they got it down to 0.4. And they're actively looking at why it's 0.4 and not 0.2 at the moment. So they're a tiny team, but they're a really active team. So the really interesting bit about it is the fact that you can pass in, it's a slightly weird syntax. You use the square bracket syntax to pass in the numpy arrays instead. So we have complex square brackets and int square brackets for these 8 bytes, so doubles and long int numpy objects. And then if we do a comment OMP parallel 4 and tell it to use the dynamic scheduler, you can pass any arguments to OMP that you'd normally see in the C world. And you have a slightly longer compile string, but it's just on their man page. We end up dropping down to 0.1 second. So that's using all the 4 cores efficiently, but the code is not quite as efficient as Cython's output yet. But all you had to do was just add these 2 one-line definitions. And so I think that's really interesting. There's a lot that's going to come out of this. I've been playing with PyPy recently, so you all know PyPy. PyPy on Python 2.7 code, basically it just works. If you're not importing external C modules, so you're just staying within the Python ecosystem with regular Python-coded modules, for example, doing Django websites or doing small CPU-bound problems, then it's pretty great. It just works. There's a tiny startup cost. Its memory usage defies any heuristics I've gained over the years. They've got some clever strategies for unboxing when necessary, and otherwise storing bytes rather than the higher-level Python objects until necessary. But at the same time, it can use more RAM. But I know of people using this in production where they've replaced servers by switching PyPy away from regular Python. So that side of things works just great. There's little support for hooking into C extensions, so you can't use regular numpy with PyPy, and this is a point of interesting discussion in the community for those straddling those worlds. But things like the multiprocessing module and IPython, they work just fine. You just plug them in, just install them, they run. So rather than doing Python pip install, you just do PyPy pip install, and then these things work. Running my earlier list version of the code, PyPy ran it in 0.3 seconds, so that's great. It runs super quick. There's a numpy branch which is being re-implemented in PyPy. It's definitely incomplete at the moment. There are some bugs in there. The team are pretty quick at fixing those bugs, but in my experience so far, the numpy code doesn't run as fast as regular numpy code. It can be a factor of 2 or more slower. So I don't think it's useful right now. It's interesting to experiment with. The fact that there are bugs hidden away in there, I'd strongly suggest that you have a good unit test suite just to validate the code that you're running, so you're really on top of it. When I ran the CPython example with the numpy code, so that's not compiling anything, this is using CPython on numpy, doing 1 million dereferences into the numpy array. That dereference is really expensive, and so the whole thing takes 50-odd seconds to run, which is horribly slow, and numpy gets it down to 5 seconds. It's not the same as the 0.2 seconds of the other examples. I'm not sure why it's slower than the compiled examples. I suspect it's because numpy is respecting the dynamic nature of the dereferences that it's doing, rather than doing the static compilation that all the other options are doing. But I haven't got to the bottom of that particular difference in speed yet. If anyone's got opinions on that, please come and find me later and inform me. Last example, Numba. So this is continuums, contender into the set of just-in-time compilers. This is also pretty cool. We just do a one-line change again. You add a decorator. And then Numba uses the LLVM toolchain to dynamically look at your code during execution and then to compile it and optimize it. And they do have support for OpenMP. It's not in I think, the current public release. I couldn't find it in there. But I know that prange exists, so the parallel range operator. And they're talking about having support for the GPU. That's because with the LLVM toolchain, you've got a large unified toolchain, and so you can sit on the back of anyone's work, for example, outputting, rather than machine code, outputting code that will go off to OpenCL. So they've got some GPU support in there. My runtime here with Numba, just that one-line change was 0.4 seconds again. It only works off numpy data. It won't give you any improvement with Python lists, so it needs the numpy stuff. And there's some Python 3 support. A couple of lines here are commented out. Each time I use Numba, the API has changed a little bit, and a few things have just changed for whatever reason. I couldn't get abs to be recognized for some reason, but if I expanded the math, it worked just fine. And in the current release, due to the rewrite they're going through, you can't allocate new arrays inside a function that's being number jitted. Before you could, and I imagine shortly we'll be able to again. So just be aware that if you're using Numba, it's still quite dynamic in its evolution. So coming up to some conclusions. So trade-offs, well, PyPy, there's no learning curve. You just use it. There are some use cases of code which works well in Python, but works poorly in CPython. I believe due to ref counting, you want to open files in a context manager rather than other ways, but I forget the details. There's a couple of things that are documented. It's all really obvious. It's all perfectly normal Python. It's just idiosyncratic ways of writing code that works in CPython doesn't work so well with PyPy. But apart from that, it all works. Shared skin, super easy to use. You get a big win because it will just compile down to C, single-threaded. I've tried hacking the C code to get OpenMP support before, and I failed when I was messing around with it. I'm pretty sure it's possible. I'm not quite sure why I didn't get it working. So it's very easy to use, but it only works if you're working with non-numpy data. Cython, so if you're just doing Cython on pure Python, then it's easy to learn, easy to use. You get a great big speed up. And Cython with OpenMP and numpy, definitely days to learn. So it's hard to get a team to use it, and it's hard to get the general background knowledge required to debug it, say. But if you want the best way to exploit the CPUs available to you, this is definitely the way to go. Numba and Pythran, a couple of hours to learn tops. Installing Numba is a pain. Numba requires LLVM. LLVM requires a billion other things. And to install those, when I'd spent over half a day on my 4-core i7 laptop sitting there compiling and failing to get most of the way through whatever the process was, I gave up, and I downloaded Anaconda. Anaconda, their distribution. That makes it really easy to use, which is great, but then you've got a dependency on an entire new distribution. So there's a team cost involved there, a deployment cost, certainly, which might be too great to bear, but for research code, it's definitely worth playing with. Pythran requires a couple of libraries, a modern boost, and that's about it. It took me 15 minutes to get that installed. I really think Pythran with the OpenMP support is something interesting to watch. If you're doing short projects where you want to get a quick win over many cores, then definitely you get an easy win there. And I haven't mentioned numexpr, which is written by Francesc, who was talking earlier. So numexpr compiles your numpy arrays and then vectorizes them intelligently. So it works on just in regular Python code. That's a nice, easy way to get better cache performance out of large array operations. So if you've got large arrays and you're working with numpy, have a look at numexpr. Oh.
The original author of numexpr. The original author is David Cook. Yeah, thank you.
David Cook.
Yeah.
I didn't know that. Okay.
He disappeared like 5 years ago.
Right.
I don't know nothing about him, so I took the package and I maintain it now.
Oh, okay. Okay. Okay, well, Francesc is not the creator, but he is the maintainer. I am nonetheless happy because I've used it in production and it works very well. So, David Cook. Okay, and so to wrap up, I think we need richer profiling options. The fact that it's not so rich a world of tools right now means it's easier to ignore doing it, which means you spend more time hypothesizing or maybe more time just ignoring and going with your gut, which is almost certainly the wrong option. So I think we need more profiling tools. 4 cores is commonplace. 12 cores, that costs a couple of $1,000s right now for 12 physical cores. And then you can get sets of motherboards which will be unified by Unix or Linux and presented as one machine. So we have many cores. Dealing with the requirements of many core computation and locking and sharing resources is hard. So I really think moving away from hand annotating code, if possible, to avoid that loss of agility, and then using JITs and any automatic compiler technique, given that they give pretty good results right now out of the box for almost no effort, I think that's a really interesting point that we should be considering, because what's that final point that I make? What the hell did I mean there? So yeah, cost of CPUs is cheaper than cost of human time. So you don't want to be burning human time, particularly lowering team velocity. You want to keep your team velocity high and probably just spin up a few more CPUs because overall that's going to be cheaper for you. So I think that's the outcome of all of this. There's some interesting alternatives. Armin is playing with software transactional memory inside PyPy to get rid of locking, where you have to do your own locking, and instead it will deal with memory changes a bit like transactions in a database. It's a really interesting idea. I'm not quite sure where that's going to come, and that's not ready for use right now as far as I can see, but that's certainly going to change things when it comes out and as and when it works. But in the meantime, I'm pretty sure that's the landscape of what works right now for high-performance calculations in Python. I'm very happy to talk to any of you if you're using Pythran or Numba in production, because I want to get some more use cases. And otherwise, I'm just always happy to chat about this stuff. So thank you very much. How much time do I have?
About 5 minutes.
Okay, a couple of questions. Yes, it's definitely worth doing profiling on the compiled code if you want to understand what's happening in the compiled code. So, and it's a bit difficult. You have another set of tools because then you're looking at profiling at the C code level rather than the Python level. That's something I'm not covering in the book, and I feel a bit remiss by not doing that, but it's a whole nother layer of pain and understanding to go through. If you've got experience profiling C code, then sure, you should definitely think about doing that. Some of the tools, so Cython gives you an annotation option. With the annotation option, you get an HTML output showing you your lines of Cython code colored from white to yellow. If they're yellow, they've got many lines of calls back into the Python library. And if they're white, they've got no calls into the Python library. It's all pure C. So the game is to turn all the yellow lines into white lines where possible. And if you can do that on your innermost loops, although you don't get any performance figures, you pretty quickly you figure out which yellow lines are important and you want to get rid of them, normally by moving to numpy if you're doing numeric calculations. And then you can get rid of most of this yellow scaffolding. And that means that it's compiling on the C side with no links back into the Python side, so no need to hook up with the GIL, and then no need to have slower performance overall. I have no opinion of CFFI. I've only ever heard good things about it, but I haven't played with it myself. So it's something else on my list, and I'd love to have time to play with it, and I haven't got around to it yet. But I genuinely have only heard nice things about it from people who have used it. So I think it's a good thing. So I've got a process from going years back with Cython where I just tend to use named files in a set of named directories where I work through, I can version control it instead, but by having them all lined up in different directories, I can compare the HTML output, and then I can marry up the different amount of yellow with the runtimes that I'm measuring, and then I can get an intuitive feel as to how changing the yellow in this part gives me a better result. So I keep a trace of everything there, but it's just a better workflow. David? So you're recommending Visual Studio as a debugger and profile at the C level? Okay. Do you have a Linux recommendation? Or is it? Does anyone have a Linux recommendation? Oh dear. Google Perf Tools.
You can use those to profile down.
Okay.
At least profile the
Yep. Okay. So, yes, you're right. So that's because the author hasn't implemented the memory view interface necessary to look at the bytes behind, so numpy has a Python level, and behind the scenes it has a C level, which contains all of the data. That's exposed via a couple of interfaces, memory view is one of them. Cython can look at that interface because code was written specifically to look at that particular interface. So rather than seeing the higher level Python object, it can see the raw bytes behind it. And as long as you stop the global interpreter lock, so you use the no-GIL operator, then you can access those bytes and guarantee that you're not messing these bytes around in any way that's going to conflict with the Python runtime. With Shedskin, that hasn't been implemented. I don't know why, but it hasn't been. There's some work and it's specialized. That's all I know. All right, I better call it there before any more hard questions turn up. Thank you very much.